So we're going to cover a couple of things this morning. We're going to look at Boolean Algebra and number systems. So Boolean Algebra is the algebra of logic gates. Now there are four operations, or mainly four, that we need to worry about. So we've got the AND, the OR, the XOR, and the NOT. And all Boolean operations are a combination of these. Okay? And it's the same as in maths. In maths you have four operations: plus, times, minus and divide. And it matters which order you do it in. So remember your BODMAS, you have to do your multiplication or division before your plus or minus. It's the same in logic. You need to do ANDs before you do ORs. Okay. Now each of these statements here has an associated Boolean symbol operator. Okay. So in the case of AND, we use a dot like that. So that means A and B. Okay? And so it equals something. So Q is, quite often we use Q as being an output. However, it doesn't have to be Q, it could be something else. OR is similar, but it's A plus B. And XOR is slightly different than OR. So we write A plus with a circle around it, B is Q. Okay, now for those of you who have done computer science, you'll see that they use different notation in computing than we do. Please try and remember in the exam to use this notation rather than the computer science notation. For a NOT gate or an inverter, there's only one input, and you put a bar over the top to indicate that it's inverted. So that means not A. Okay? So the gate symbols for these are like this. Okay, so they're the corresponding gate symbols. All right, so if you haven't got a copy of this down somewhere, then it's probably a good idea to copy this down now. Now the next thing is how do we use several gates together to produce a single output? And I'll show you an example where we take the A and B and we want to produce a NAND gate. So we want to produce the inverted output of A and B. So that would look like this as a circuit diagram. So here's my A and B, and I want to invert it, so I draw my symbol for the inverter, and that's going to be Q. Okay. Now if I've inverted the A and B, well that's just a NAND gate, isn't it? And I can represent a NAND gate as A dot B with a bar over the whole thing is equal to Q. So that means that I've ANDed A and B and then I've inverted the output of that. Okay? Now quite often you might see some intermediate variable in the middle there. So in this case I've labelled this one C. That is not going to take place in any of my Boolean operations. Okay, so C doesn't actually take place in my Boolean algebra operation there, but it is an intermediate variable which if I were to build this on a circuit, like using NAND only or something, I might be able to measure that point. Now it's quite often it's easier if you've got, especially you've got a complicated circuit where you've got these intermediate variables where if you know the variables at that point, the states at that point, then the output of that you can quite easily find because you just look at, you can ignore what they are if you know that the logic at this point, you can ignore what's preceding it and just do the logic for that part. So it's a way of breaking it down into manageable chunks, if you like. So I could do the same with any of these gates. I could take an OR gate and invert it, like so, and that would be a NOR gate. We'll have it the same as an OR gate, and A or B inverted. So I put a bar at the top like that. Okay. So here's just some examples. I'm going to go through a more complicated example in a moment and show how we can take a circuit diagram and write the Boolean expression for it. So I'll draw one up quickly. Okay, so in this case, I have three inputs here. So I'm going to have three variables in my Boolean expression, A, B and C. And it's going to be equal to Q, my output. So my Q is going to be equal to something to do with A, B and C. Now in this case, I've got A is ANDed with B, because both of those are connected to the inputs of an AND gate. So let's just write that down, A dot B, and then that is ORed with C, because the output of that AND gate is then being ORed with C. Okay? Now remembering before I was saying there's an order of operations, and that means that if I were to think of the OR being like a multiply, the AND being like a multiply, and the OR being like a plus. So if I had 1 plus 1, let's do a better example, 3 times 2 plus 4. Well, how would you do that? Is it 3 times 6, or is it 6 plus 4? So order of operations matters for this. Alright, so 3 times 6 is 18. So if I just went 3 times, and I got the order of operations wrong there, then I get the different answer than if I did 3 times 2, which is 6, plus 4, which is actually equal to 10. Because I have to do this part first. I have to do the multiplying first. It's the same in logic. I need to do the ANDs part first before I do my ORs. So if I have this circuit here, this is being ANDed before it's being ORed with my circuit. So going from left to right, you can see that the AND gate is being processed before. I need an output from my AND gate before it gets ORed. So let's draw the logic, the Boolean algebra statement for this gate, or this circuit, which is slightly different. So now I've still got my three variables A, B and C, but in this case I'm ORing A and B. So A or B first, and then taking the output of that and ANDing it together. So A or B is then being ANDed with C. However, I need to differentiate that from what I had before, because that's going to produce a different output for a given set of inputs than the other circuit. So what I need to do is indicate that I'm doing the OR part first, and then doing the AND after that. Now, in maths, what do? If you want to add something together and then multiply it, you want to make sure that it's being added first. What do you put around it?
Brackets.
Brackets. So I'm going to put some brackets around my OR statement there to show that this part is being ORed before the output of that has been ANDed with C. Okay? And so that will allow me to say definitely that this is the logic statement for the Boolean statement for this circuit. Quite often you're asked to draw a circuit given a logic statement or a Boolean statement like this. So we're going to do the same thing but in reverse. And so I'm going to write a statement and we're going to draw a Boolean algebra, a logic circuit from it. So if I have A, X or B and C, and I'm going to bracket around it like that. Not terribly different from what we had just a minute ago, but you can see that I've got my A, X or B is done first. So I've got my three inputs, A, B and C. So that's the first thing I do. And that's going to be equal to some output Q. And so in between here is going to be some network of logic gates. So I've got my A, X or B in brackets. So that means that's the thing I do first. So I'm going to draw that first. Draw an XOR gate with A and B as the inputs. And so this output here would be whatever this whole bracket is. And that's being ANDed with C. So I draw an AND gate down to the right of that, with the output of the XOR gate being ANDed with my C. And there is my circuit diagram. Okay? So to take a Boolean statement and create a circuit diagram, you just need to remember which operations are being done first, or recognise which ones are being done first, and basically do them first. So you start with all your variables, and it might be sensible if you know that things are being done together, have them next to each other. So if that was A, X or C, having it like this probably wouldn't be particularly easy, particularly useful, because I would need to have C coming up to here, and it's going to be a bit messy. Okay? Right, has everybody got any questions about Boolean statements and then how to draw a diagram from it? Okay, alright, the next thing we're going to look at is something called number systems. Now this one's reasonably important because you are expected to be able to do this kind of stuff on the exam. They're very common, comes up on exams. Okay, so what's the number system that we commonly use called? Anyone know what that is? Do we commonly count with binary, do we? Yeah? Decimal. Decimal, isn't it? Decimal. So, and how many different number systems do we count? How many different symbols do we have in decimal? So if we were 1, 2, 3, 4, 9. Is there one missing from that lot?
0.
0. Okay, I've got to put the 0 on this end. Okay, so how many different symbols are there? 10. Okay, so we've got 10 symbols. And what that means is I can represent 10 different values with just using one symbol, because I've got a different value for every symbol. So this symbol represents a quantity of 0, so nothing. This represents a quantity of 1. This means I've got 2. Okay, so I can represent how many, if I'm talking about how many apples have I got, if I only want to use one symbol, I can have up to 10 different amounts, including 0. So if I want to use more than 10, so if I've got more than 10 apples, so let's say I've got 12 apples, what do I need to do? Can't use one symbol anymore, can I? So if I've got 8 apples, I can just write 8, right? It's one symbol, done. But if I've got 12, how many symbols do I need? Another one, don't I? I need 2. Okay? So in the example 12, what does that number there mean? What does the number, or the numeral 1 in this number 12 mean? means we've got one lot of 10, doesn't it? Okay, so one lot of 10. And what about this one here? What does the numeral 2 mean in 12? 2 lots of 1, doesn't it? 2 lots of 1. Okay? And so basically what's happened here is that when we get to 9, we go up to the next one by getting a second digit for a start, and that's the first one that's not 0, and then clocking back the last digit all the way to 0. So you sort of think of it being like a clock, the old analog clock, but instead of having 1 to 12 on it, it's got 0 to 9. All right? When you get to 9, you go back round to 0 again. Okay? But the next one ticks over 1. So you go around one more, so on. Okay? So every time you go around a lap with the units, in this case, so this is your units, and this, every time you do a lap of units, so once you get to 9 and go back to 0, that's a lap, then you increment the tens by 1. And if you do that enough times, get to 99, what's the next thing you're going to increment? The third number, which is the hundreds, isn't it? Okay? And then you've got the thousands, then tens of thousands, hundreds of thousands, and so on. So each of these digits in a number has a value that is related to a power of 10. So if I had the year 2015, that means we've got 5 ones plus 1 10 plus 0 100s plus 2 1000s. Okay? So the number 2015, I can add my units times that digit. Okay, so ones times that digit, tens times that digit, hundreds times that digit, and thousands times that digit. Okay, and if I do that, I get the number 2015. But breaking it down, this is how it works. Now in electronics, in digital electronics, we've only got on and off, haven't we? We can only say the LED is on or LED is off. We don't really say it's half on. So how many states does that allow us to have? 2, isn't it? Okay. So if we've only got 2 states, that means that we can only represent it with 2 symbols. So before if we had 10 numbers, I could represent each one, or 10 values in a symbol, I could represent it with 10 symbols. Okay? But now I've only got 2. So be this one and this one. So I can't use the numeral 2 in a binary or digital circuit, or represent a digital number. So if I were to get rid of that lot, I don't have 10 symbols anymore, I've only got 2 symbols. And those 2 symbols, the 0 and the 1, I can still represent any number I like with it, in the same way that I can represent any number I like with 10 symbols. I just need to be a little bit more creative about it, and a little bit more analytical. So if we were to count up in decimal, we go 0, 1, 2, 3, 4, 5, till we get to 9. And when we get to 9, we clock back over to 0 and increment the next one up by 1. Okay, so let's do that over here in decimal. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And now we've got our second digit incrementing by 1. You can also, if you like, think that there is a 0 in front of them, but you quite often don't write that. Okay, and now, so I'm going from 0 to 1s now. 1, 1, 1, 2, and it's not until I get to 1, 9 that I increment it to 2, 0. Okay, so I'm pretty sure we've all got a pretty good grasp of how to count to 20 or so. But what I'd like to do is take that thinking and we're going to apply it to, instead of 10 symbols, to only 2. So now, if I were to count, start with 0, right? And then we go to 1. Oh, but hang on, I've run out of symbols. I don't have a numeral 2 like I did here. So it's as if I was at 9 already. And then what do I have to do when I get to there? The next one I have to increment. I have to flip that one back to 0 and increment the next one. So this one becomes 0. That. Okay? And now I increase this one by 1 as well. So that's really no different. Oh, but hang on, I've run out of digits here again. I can't go to 2 or anything else. I have to go back to 0 and increment this one by 1. Oh, but it's the same thing. That's kind of like I've reached 99 now. So I've got to flip back to 0 and increment again. So I need another digit. So you can have a look at this. These are actually the same value. That's in decimal. This is in binary. So 5 would be, I'll increment that one by 1. That one stays, that one stays. Oops. Okay, that would be 5. And 6 would be like that. Okay? So as you can see, it's the same way of counting up as you do in decimal, except when you get to go to 2, well, that's, you don't have a 2, so you have to increment as if you were at 9. Right? So there's only 2 states that you can have. There's only 2 numbers you can, or 2 numeral symbols you can use, and so you have to increment quicker. And so you can see here that even when I go up to so 7 is 1, 1, 1. 8 is going to be 1, 0, 0, 0. 9, 10, 11, 12. Okay, so you can see how it follows. And once I get up to 9, you can see that while I'm using only 1 symbol for 9, I need 4 symbols for 9 in binary. Okay? So I just, because I've got fewer states, it means I need more symbols or more digits in my number to represent the same amount of things. Okay? So that's how you count in binary, and this is the reason why binary works. Now there is a couple of things that you notice about binary, you might notice about binary. So when you've just got a single 1, so all the ones that only have a single 1, I'm going to put a little arrow next to it. That one's got a single 1. Right, and I don't have any more. Okay, so the first one that has a single 1 is just 1. Okay, so I'm just, when I say the number, I'm going to talk about it in decimal. So this one here is a decimal value of 1. This has a decimal value of 2. So what's the difference between 1 and 2? Well, what's the factor between 1 and 2? If I multiply 1 by what to get 2? 2, isn't it? Right, the next one that has just a single 1 in it is 4. Okay? And what do you notice about the position of the 1 here? What's common about the position of the 1 on each one of them? It's the leftmost, isn't it? Okay? So in this case, a 4 is a factor of what greater than 2, which is a factor of what greater than 1? 2, isn't it? Okay, so there's a common factor there. This is twice as big as that one, and this is twice as big as that one. And so what do you think the next one is? If I didn't tell you what it was, what do you reckon the next one would be? 8. Okay, and if you look, 8 is this one here. There we go, there's a single one on the leftmost, and it is twice the size of 4. Okay? And so each of these bits, each of these values of each of these ones here is just a factor of 2 greater than the next one. In the same way that in this one, this is my tens, ones and hundreds there. So there's a factor of, what's the factor between each place value there? 10, isn't it? Because we've got 10 symbols. So this one needs to have a value of 10 more, or 10 times this one. This one needs a value of 10 times this one, and so on. Well, in this case, we've only got 2 symbols, so each one of these digits here has to have a value that's 2 times more than the one to its right. Okay? And so, if we were to look at the values of each place part in decimal, I could write it like this, and the next one would be thousands, oops, 0 there, and tens of thousands and so on. Alright, so I could write down the place value for each decimal point, or each numeral in a decimal number this way, and I could do the same thing in binary. But the reason why I might do that is so that it's easier to decode a decimal number into binary, or a binary number into decimal. And I'll show you how we do that in a minute. So, in the same way that if we've got ones, tens, hundreds and thousands, what do you think it is for binary? So we've got the first one is ones. What do you think the next one is? Remember, it's not a factor of 10 anymore, it's a factor of 2. So it's 2's. And the next one is a factor of 2 greater than that. 4's, 8's. What do you think the next one is? We haven't covered that one, but it'll be 16, wouldn't it? 2 times 8 is 16. So our place value for a number here would be ones from the right, 1s, 2s, 4s, 8s, 16s. Then 32s, 64s, so on. Okay? And so, if I have a binary number, let's start with 1, just a random one. So there's my binary number with 5 digits. I can actually work out what its value is in decimal by simply adding up how many 1s I've got. So it's a 1. I've got no 2s. I've got 1 4. I've got 1 8. And I've got no 16s. So 8 plus 4 plus 1 is 13. So this number here in binary, so to represent, to indicate that that is a binary number, I put a little subscript 2 at the end of it. Okay? So that means that it's a binary value. Now I can convert that into decimal by doing this process. So I find, okay, I've got one lot of 1s, no lots of 2s, plus one lot of 4s, plus one lot of 8s, plus no lots of 16. Add them all together and I get 13. And to indicate that it's decimal value there, I'm going to put a subscript 10 after it. So that's how you can convert from binary to decimal.